Hi, and welcome to the Geology module for the Foundations of Science course. In this module, we'll be looking at the concepts of geology like plate tectonics, and seeing what they can tell us about the lost continent of Atlantis. We hope that by the end of this module, you'll be able to do the following. Over the course of human history, there have been many lost civilizations, including the ancient Greeks, Egyptians, and Mayans. Despite their advanced technology and political systems, each of these rich cultures perished due to war, colonialism, and economic collapse. But have you ever heard of a civilization disappearing into thin air? Or even more fantastic, sinking underwater? Most of us are familiar with the legend of Atlantis, the lost continent which sunk beneath the sea thousands of years ago. The first mention of Atlantis was around 360 BC in the works of the famous Greek philosopher Plato. The story goes that Atlantis was a powerful empire that conquered most of Western Europe and Western Africa around 10,000 BC. As the Atlanteans became more and more powerful, they became increasingly corrupt and greedy and decided to attack the city-state of Athens. This angered the Greek gods, who forced the sea to rise up and swallow the continent, causing Atlantis to disappear forever. As fantastic as this legend is, people throughout history have taken it as truth and have actually searched for the lost continent of Atlantis. In fact, there are rumors that it lies beneath the Mediterranean Ocean, the Caribbean Sea, or even underneath the ice of Antarctica. While the archaeological evidence suggests that Atlantis is nothing more than a legend, in this lecture we want to take a geological approach to this mystery. Is it really possible for an entire continent to sink into the sea? In order to answer this question, the first thing that we need to understand are the geological properties of a continent. One of the most common misconceptions about landforms such as continents or islands is that they are like massive rubber duckies floating on top of a layer of ocean. If this were the case, it would be easy to imagine a scenario where a continent could sink and disappear into the sea. However, the Earth is simply not built like that, and as you'll learn in this lecture, the continents and the ocean floor are actually part of the same layer of the Earth. To get a better understanding of what continents are and how they behave, let's take a closer look at the composition of our planet. I'm sure many of you have seen this image of the cross-section of the Earth. In general, there are two ways to think of it. First off, you can look at them with regards to the three main layers, which geologists talk about varying in composition, or you can look at it with regards to five main layers, which vary based on physical properties. When the Earth was formed, the different types of materials that made up the planet began to separate according to their density. Have you ever shaken a bottle that had oil and water in it? What happens? The denser water sinks to the bottom, while the less dense oil rises to the top. Why do helium balloons float? Because the helium is less dense than the nitrogen and oxygen-rich air of our atmosphere, so the balloon floats. Just as liquids and gases can separate because of density, so can solids. The same process of density separation happened to our planet over the course of billions of years. Because of this separation, the uppermost layer of the Earth is made up of relatively less dense materials than the interior rock and core of the Earth. And while you might be thinking, hey, rocks are heavy, these rocks are actually much lighter than the heavy metals like iron and nickel, which make up the Earth's deepest layer, which is called the core. There are two levels which make up the core of the Earth, each with different physical properties. The inner core is around 800 miles thick and made up of solid iron and nickel. The inner core is extremely hot, reaching temperatures of up to 9,000 degrees Fahrenheit, and under intense pressure from all of the layers of Earth above it. In fact, the pressure down there is almost 3 million times the pressure on the surface of the Earth. For this reason, the atoms are not able to flow freely. The outer core is around 1,400 miles thick and is made up of liquid iron and nickel. The outer core is also under intense pressure from overlying layers and is very hot, around 4,000 degrees Fahrenheit. The pressure and temperature conditions of the outer core are just right for iron and nickel to become liquid. So while the inner and outer core are made up of exactly the same material, they're in two completely different states. One is solid while the other is liquid. The next layer of the Earth is called the mantle and is the largest layer of the Earth with a thickness of 1,800 miles. It's composed of very hot and dense solid rock. Although it might seem strange, solids can flow in the same way that liquids and gases flow. The process is just much slower for solids. This may seem confusing at first because we don't think of solids as being able to flow. One way to imagine the flow of mantle is to picture a layer of chewing gum or taffy that's being pushed around. Taffy is solid, but it can still move as a layer. This flow occurs because there are tremendous temperature differences, around 2,500 degrees Fahrenheit, between the top and bottom of the mantle. The rocks in the lower part of the mantle are much hotter than the rocks in the upper part. Even though these rocks are the same composition, the lower, hotter rocks are less dense than the rocks above them, and less dense materials will always rise. Once the hotter rocks reach the top, they begin to cool down and eventually sink back to the bottom of the mantle. The process takes many millions upon millions of years. This continual process creates what geologists call convection currents. In fact, if you have ever boiled water for pasta, rice, or noodles, you've seen convection currents in action. Check it out. The outermost layer of the Earth is called the crust, which is extremely thin in comparison with the other layers. The crust, along with the uppermost components of the mantle, together make up a layer called the lithosphere. Crust and mantle refer to the composition of layers, while lithosphere refers to the physical properties of this outermost layer. The lithosphere is broken into many pieces called tectonic plates, which move on top of the slightly squishy mantle below, not the ocean. This is an important point. The continents and the ocean floor, plus the material that lies beneath them, together make up tectonic plates, which move above the mantle beneath them. The ocean in all of this sits on top of the tectonic plates. There are two types of plates, continental and oceanic. Continental plates are made up of continents, which are mostly composed of granite. Mantle rock lying beneath the continents, and often some ocean floor and underlying mantle, made up of rocks called basalt. Oceanic plates are made up of ocean floor and mantle rock beneath. Interestingly, the granite that makes up continents is much less dense than the basalt that makes up ocean floors. Continents sit so much higher on the planet than ocean floors because of this density difference. In order to understand how these different plates interact with each other and address the question of the lost continent of Atlantis, let's take a closer look at the theory of plate tectonics. Although you may not be able to feel it, the continent that you live on is actually moving right now. That's because tectonic plates are constantly, albeit very slowly, moving relative to each other. Geologists believe that over 200 million years ago, the 7 separate continents on Earth today existed as part of a large landmass we call Pangaea. Over time, the continental plates making up Pangaea spread apart and now exist in the arrangement we're familiar with today. Currently, there are around 30 continental and oceanic plates that you can see here. However, this number is not consistent because depending on how the plates interact with each other, it's possible for a plate to be destroyed or a new plate to be created over long periods of time. It's these various interactions which result in earthquakes and/or volcanic activity along plate boundaries. Until now, we've really been thinking about the compositions, or the physical properties and behavior of continents on a planetary scale. We know that both ocean and continental plates slowly move away and towards each other because they sit on top of a squishy layer of mantle. But in order to understand how exactly two plates interact with each other, we have to look more closely at their densities. Density is an amazing property. If you can understand density, then you can really understand why Earth materials, like tectonic plates, move on and within the Earth. Remember when we talked about the oil and water example? Some of the principles from that example apply to the Earth's plates as well. As you'll see in the coming slides, there are many ways plates can interact with each other, all of which are dictated by a plate's density. So we've talked about density, but we haven't really defined it. You can think of density as the amount of stuff in a space. Less dense material contains less stuff than more dense materials. You can also think of density as the number of particles that are packed into a fixed volume. The density of a material can be affected by 3 things. 1. Composition, 2. Temperature, and 3. The amount of pressure acting on the material. There are 2 aspects of composition that might affect a substance's density: the type of atoms it's made of, and how those atoms are arranged. An example of the type of particles that you are packing is like if you squeeze 10 humans in a room versus 10 elephants. The packing of the elephants would result in a denser room. The same is true for atoms. If you pack in heavier atoms, you get a denser material. This is why the iron core of the Earth is at the center of the Earth. It's much denser than the lighter granite and basalt that make up the Earth's exterior. When we think of how the arrangement of particles affects density, we can think of that same example of filling a room with people. You could pack more people in a room if they stand with their arms pressed against their bodies than if they stood with their arms and legs splayed out. The room with more people packed into it would be denser. This is why diamonds in your rings are much denser than graphite in your pencil. They're both made out of carbon, but diamonds contain many more carbon atoms per volume than graphite. Temperature is a property that affects a substance's density. The hotter a material is, the faster the molecules that make up that material are moving. Higher temperatures mean faster particles. Higher temperatures typically result in substances having a lower density, because the increased temperature tends to increase the volume of the substance. There are some exceptions to this rule, for example water because of its hydrogen bonding. But for rocks, higher temperatures result in a decrease of density. Remember that rocks at the bottom of the mantle are much hotter than rocks at the top. The rocks at the bottom are less dense and rise, and the opposite is true. The rocks at the top are colder and more dense, and so they sink. The last property that affects density is pressure. Higher pressure generally results in a denser material because pressure forces atoms and molecules to pack together more closely. This is kind of like what happens in a trash compactor, where the compacted garbage is much denser than the starting pile of trash. Next, we'll take a look at how the plates of the Earth interact. Remember to keep in mind how density affects materials, and the fact that less dense material will always rise relative to more dense materials. Also think about how the three physical properties that affect a plate's density can affect the outcome of two plates' interactions. There are three types of plate boundaries, defined by the way the plates interact with each other. A transform boundary is defined by two plates sliding past each other. This type of movement is capable of creating earthquake activity. The San Andreas Fault in California is a good example of this type of plate boundary. We won't be discussing transform boundaries much more in this lecture, but we wanted to make sure that we at least mentioned them. Let's focus on divergent and convergent boundaries. The second type of plate boundary is a divergent plate boundary, which is when two plates move away from each other and can result in one of several geological formations. When continental plates diverge, they usually produce a rift valley, such as the East African Rift Valley shown here. However, the more common type of divergent plate boundary is between oceanic plates, which result in an oceanic ridge, such as the Mid-Atlantic Ridge shown here. When two ocean plates diverge, the reduction in pressure on the underlying mantle causes the solid mantle to melt, resulting in magma rising to the surface. This creates volcanoes along the divergent boundary. On the ocean floor, this magma rapidly cools, solidifies, and becomes new oceanic floor. When two plates move towards each other, they form a convergent plate boundary. At convergent boundaries, one plate can be pushed beneath the other, or two plates can collide and essentially squish together. How two plates interact once they come in contact depends entirely on what type of plates they are and their relative densities. If an oceanic plate converges with another oceanic plate, the older plate will always sink beneath the younger plate and form what geologists refer to as a subduction zone. This is because the older oceanic plate has had longer to cool down since its formation. Remember, colder materials sink relative to hotter materials. So older plates are colder and therefore more dense than younger plates. The sinking of the solid older plate into the solid mantle is hard to imagine, but it happens. Solids can slowly move into other solids if we have enough time. The sinking of a tectonic plate into the solid mantle causes the mantle to melt. This melted rock is called magma. During this process, the newly formed magma, now less dense than the solid mantle rock around it, rises to the Earth's surface and is released from volcanoes that erupt through the overriding younger tectonic plate. If enough magma is released, these underwater volcanoes can grow big enough to poke out of the ocean, creating a volcanic island. A famous example of this type of convergence would be Japan or the Mariana Trench near the Mariana Islands. If an oceanic plate converges with a continental plate, the oceanic plate will always subduct underneath the continental plate and into the mantle below. As we mentioned before, continental plates are made up of materials like granite, which are much less dense than the basaltic rocks which make up the oceanic plates. This means that a continental plate can never sink underneath an oceanic plate. The same processes that result in volcanoes along ocean plate to ocean plate subduction zones causes volcanoes to form on continents. Basically, magma resulting from melting mantle rises, breaks through the overlying continental plate, and produces chains of volcanoes. A famous example of this is the area along the western coast of South America, where the Oceanic Nazca is being subducted beneath the continental South American plate. The last combination is if two continental plates collide. And if two continental plates collide, they will compress against each other, with the interacting plate boundaries forming extensive mountain ranges. Why can't a continental plate subduct under another continental plate? The answer is density, of course. The underlying mantle is so much denser than the continental rocks that continents simply can't sink into the mantle. A good example of this is when the northern boundary of the Indian plate collided with the Eurasian plate, lifting up to form the Himalayas. As you can hopefully see, there's just no way for an entire continent to sink underneath the ocean, because continental plates are less dense than oceanic plates and would never subduct under them. Continental plates are also much less dense than mantle rocks, and cannot sink into the mantle. We would never have an entire continent become lost in the ocean. However, there might be another explanation for a civilization disappearing underwater overnight, or at least an entire city. In the late 1600s, the seaport town of Port Royal in Jamaica was literally washed away into the ocean due to a number of cultural and geological factors. In the years before the disaster, the town was expanding so rapidly that they began to fill in areas of water with dirt so that they could build on top of it. In addition, they built their buildings very tall and out of heavy materials, which made them extremely vulnerable to any geologic activity. In 1698, a large earthquake occurred nearby in the ocean, and the subsequent tsunami caused most of its northern section to wash away into the sea. Additionally, rising sea levels could cause parts of land masses to disappear under the water. As shown in the recent sea level rise graph, since 1880 sea levels have raised an average of 20 centimeters, or 0.2 of a meter. Land mass locations with an elevation closer to sea level could be in danger of flooding and eventual submersion in the future if sea levels continue to rise. An example is the coastal regions of England. This image shows what part of England's coast could look like in 200 years if sea levels keep rising at the rate they currently are. But what can cause rising sea levels? One major factor is the increased rate of melting of the Arctic-Antarctic glaciers. As this graph shows, the average thickness of the Earth's glaciers has decreased over the last 50 years. When these glaciers melt, the resulting liquid water is added to the ocean, raising its level. Now relate this back to the idea of the Atlantis problem. Could a city be submerged under the ocean due to rising sea levels over a period of many, many years? The Port Royal case brings up an important idea about the claims you are asked to believe, as well as how people state those claims. If someone had described the lost city of Atlantis, we wouldn't necessarily have a problem with that, and we might have thought that it occurred in a similar way as Port Royal. The problem with the lost continent of Atlantis is because it sets up a mechanism that is impossible. Continental plates do not go under oceanic ones. Word choice matters when evaluating claims. The more you question the exact way that terms are being used in a claim, the more precisely you understand what you're being asked to believe, and the better prepared you might be to answer whether or not you should buy that house on the beach.